Behind me is the Bendix G-15, a full-fledged vacuum tube computer from 1956. And off to my right here is the UE1, my homebrew vacuum tube computer from like 2 to 3 years ago. Both of these use a massive number of vacuum tubes, with the UE1 using around 300 and the G-15 using 460. There's not a single transistor in use anywhere on either of these machines. However, there is a lot of solid-state components in use. The Bendix G-15 has around 3,400 germanium diodes in it, and the UE1 has, I don't know, I didn't count, probably about 1,000 Schottky diodes in it. The only reason that I used Schottky diodes was because I couldn't find germanium diodes in mass. But when I was designing the UE1 here, the kind of year that I was aiming for was 1955, which is dead square in the Bendix G-15's wheelhouse. So the construction methods between the two are very close. That's especially evident in the paper tape reader up here. I built this paper tape reader completely from scratch, machining all of the components out of raw aluminum. But the design is essentially a copy of the Bendix G-15, all the way down to the fact that it uses the exact same photodiodes that are used in the G-15's paper tape reader. Right behind this little chrome box right here is 6 photodiodes. They are absolutely minuscule. We actually had one go bad when we were restoring the previous G-15 that was here, and I had to find a replacement for it, which was not easy, but I found enough to actually replace this one and allow me to build the phototape reader on the UE1 over there. But this is a vacuum tube computer from 1956 using a space-age technology like photodiodes. That's wild! But also, how does that even work? When it comes to vacuum tubes like this little 6AU6 pentode here, which is the primary tube that I used in my homebrew computer over there, I have a pretty solid idea of how these things work. But when it comes to semiconductors like diodes, photodiodes, or transistors, I've been pretty hopeless. So I've spent the last 2 days reading about just diodes and photodiodes, and I think I'm starting to get a little bit of a grasp on it. So let's start with diodes, and I actually have one here. This is a 1N4148, a small signal diode, and inside of this little tiny glass package is something called a p-in junction. That means that we have a piece of semiconductor material that's been p-doped so that it has freely moving electron holes, and a piece of semiconductor material that's been n-doped so that it has freely moving electrons, and they're pushed up against each other, and that's what creates the one-way street that allows a diode to be a diode. Now, the first time I read that, I didn't understand any of that. So let's dial it back a bit here and get a little more fundamental. So a semiconductor material is a material that's actually a pretty poor conductor. And if you use it just as it is, like a chunk of silicon, germanium, or selenium, or gallium, it doesn't really do much. You have to dope this piece of semiconductor material with an impurity. Now, there's a whole lot going on here with like valence bonds and tough physics, and I'm not gonna go that low because, we're just chasing down this. If you wanna make an apple pie from scratch, you must first invent the universe. But essentially, when you dope your semiconductor material, you're choosing very specific impurities to inject into it to give that semiconductor material an imbalance in one way or another. So for n-doping, we're going to introduce stuff like phosphorus, arsenic, antimony that creates an imbalance so that there are more charge carriers than places for those carriers to go. And then when we do p-doping, we're introducing stuff like boron, aluminum, or gallium, and this creates the opposite, an imbalance with more electron holes looking for something to fill that. So we take our n-doped semiconductor material and our p-doped semiconductor material and we push them together, creating a p-in junction. And all of the free-moving electrons in the n-doped material want to push across that bridge and go into the p-doped material to go find homes. You end up with something called a depletion zone. Essentially, you hit an equilibrium in the middle of these two semiconductor materials where all of the electrons have found homes, and the whole thing finds a kind of stability. However, if I take a battery and I hook the positive side up to the p-doped semiconductor material and the negative side up to the n-doped semiconductor material, we now have an excess of electrons flowing into the n-doped semiconductor material. So they start to migrate through the depletion zone into the p-doped material. Since we have a large positive charge over there, it's pulling them away, and you allow electrons to flow in one direction. However, if we switch it around and we put the negative side of our battery on the p-doped material and the positive side of our battery on the n-doped material, all of the electrons in the n-doped material want to go the other direction towards the battery, and all of the electron holes in the p-doped material find electrons to get filled up. Nothing actually passes through the diode because nothing ever makes it to the depletion zone. And so in this way, you have now created a one-way street. Now, every diode has a reverse breakdown voltage. Essentially, when you've got it hooked up backwards, there is a voltage level, a point at which you have so much potential difference, so much push backwards through that diode that it starts to break down and current starts to flow in the opposite direction. This is called the Zener effect or avalanche breakdown, depending on the type of materials that you're using. For this 1N4148 here, it is 75 volts, which is a lot. But as long as I don't overheat the diode by putting a colossal amount of current through it, this doesn't inherently destroy the diode. This Zener effect can be used in specific types of diodes called Zener diodes. And I have one of those right here. This one is a 5.1 volt Zener diode. That means that at any potential difference greater than 5.1 volts, the charge carriers start to break down inside of it and allow current to flow in the opposite direction. I've got that little Zener diode hooked up to my bench power supply here, and I've got the positive hooked up to the cathode and the negative hooked up to the anode. And currently the power supply is at 1.9 volts and there is no current moving. And actually I can bring the voltage up and you can see that our current stays at 0.00 as the voltage rises. But once we get to 5.1 volts, where the Zener breakdown of this diode is, there it goes. You can see now we're starting to move 200 milliamps. And then we get below 5 volts and boom, our current goes right back down to 0. So there we go. We're seeing the Zener breakdown of that diode in real time here as we crank more and more power into it. Now here's where things get really interesting, because photons, like those coming out of my little flashlight right here, are energy. And if those photons strike the semiconductor material in a diode, they can impart some of their energy into that material. Notably, if they strike the depletion zone right at that p-n junction, they can knock an electron loose, creating an electron-hole pair and pulling that depletion zone out of equilibrium a little bit and allow it to break down in the reverse direction. And this is exactly how a photodiode works. Interestingly, all diodes are photodiodes. This little 1N4148 here could be a photodiode if I could get the photons to directly strike that depletion zone. Now this is a terrible way to measure a diode, but the multimeter here is going to impart just a tiny amount of voltage onto the diode. And so I've got the positive lead connected up to the anode and the negative lead connected up to the cathode. So this is actually forward biasing the diode, and you can see that we're sitting at like 1.7 mega ohms. But if I switch these leads around and hook them up with the positive to the cathode and the negative to the anode, you can see that we're not measuring anything. So we're now reverse biased and there is zero current moving in the opposite direction. However, if I take my little flashlight here and I shine it straight into the glass package, oh, look at that. We saw it just briefly there. It's really hard to get the photons to strike that p-n junction directly, but there we go, all the way down to like 7 mega ohms there for a second. So just by putting some light onto the diode, I'm starting to change the reverse breakdown properties of this diode. Since all diodes have this depletion zone, and striking that zone with photons changes the breakdown voltage of the diode, all diodes are in fact photodiodes. But this 1N4148 is actually a really, really terrible photodiode. If you more strategically pick your semiconductor material, doping material, size of the depletion region, and maybe even add in a lens to direct the photons onto that region, you can make a much better photodiode, like this 3F42 photodiode right here, which is absolutely tiny, but this is the exact photodiode that the Bendix G-15 uses. So if we perform that same test on this 3F42 photodiode, you can see that it's currently sitting at about 70 kiloohms, and that's because the photodiode is facing straight up, and that's where the lights in the room are. If I cover this up, you can see we bump up to like 1.5, 2, 3, 5, 7 mega ohms. And conversely, if I shine a flashlight onto it, we're down into like 100 ohms. Less than 100 ohms. That's insane. Look at the range that this thing has. That's so cool. This 3F42 photodiode seems to react pretty well to the light coming out of my flashlight, but this flashlight is not an LED flashlight. There's an actual bulb inside of there, which means that I don't know if this photodiode is reacting to the visible light that's coming out of this flashlight or the infrared light that's coming out of this flashlight. And there are definitely ways to construct photodiodes to react to either. As a matter of fact, the photodiode in your remote control for your TV is often an infrared photodiode. Now, if you're lucky, all of this information can be found in the datasheet. This particular datasheet is for a Marktech NTPD2601, and you can see that there is a graph talking about relative responsivity and what wavelength that happens at. This particular photodiode is often meant for scientific use, and so the datasheet has to be quite in-depth. But there's a lot of times that you'll find a photodiode datasheet that just doesn't have a whole lot of information in it. Or worse, you'll find a photodiode and you don't know what the part number for it is. And actually, with the case of our 3F42 here, the datasheet just doesn't exist anymore because this particular photodiode is more than 60 years old. So it sure would be nice if I could figure out what these photodiodes are actually responding to. Is it near infrared? Is it visible? What is the responsivity like? I mean, the paper tape in the Bendix is moving by pretty quick. They say it can do 200 characters per second. That means that you're going to get some pretty fast transitions on the face of the diode. So it has to be able to respond pretty quickly. If only I had a tool that could tell me all of this information. This is a Bowmim DA3 Fourier transform infrared spectrometer, and the control computer for it is a PDP-1173 with 2 megs of RAM, full color graphics, and an insane vector processor. Today we're going to do science like it's 1985. Now, I said this is an infrared spectrometer, but the DA3 series is incredibly versatile. Depending on your source, beam splitter, and detector combination, it can go from far ultraviolet all the way down to far infrared and detect everything in the middle. Now, normally what you would do with this spectrometer is you would put a sample in the sample compartment, and the detector would detect which wavelengths of electromagnetic radiation are transmitting through the sample and which are being absorbed. And that can tell you a massive amount about what molecules are in that sample. But we don't want to look at a sample today. We want to look at this 3F42 photodiode. Right up here at the top, we have multiple sources that can be selected via this steering mirror, and they pass through a filter wheel, then an iris, down to a reflecting mirror, to a collimator, and then it goes through a beam splitter here that splits the beam. Half of it hits a fixed mirror here, and the other half hits a movable mirror there. They come back, recombine, shoot through the bottom, steer into the sample compartment, pass through your sample, and finally get focused on one of these 2 detectors up front. And on the left, we have the silicon detector. This is essentially a silicon photodiode that is good from 50,000 wave numbers all the way down to 8,500 wave numbers. And then on the right, we have an INSB, or indium antimony, which is good from 12,000 wave numbers all the way down to 2,200 wave numbers. Now, even though those 2 detectors give us an incredibly wide range, we actually have a bottleneck someplace else, and that's this piece right here, which is the beam splitter. This thing is made out of quartz, and it actually has a limit. It only lets wavelengths from 20,000 wave numbers down to about 4,000 wave numbers pass through it, which is most of the visible spectrum down into the near infrared. Now, like I said, normally you would have a sample in the sample compartment, but there's nothing stopping us from just not putting anything in there. And then if we take a spectrum like that, it really just gives us information about the atmosphere around us. And that can tell us some interesting things, but mostly what it can tell us are the capabilities of the machine. We can see exactly which wavelengths of light that source up top is putting out. We can see the limitations of the beam splitter in the middle. And most importantly for today, we can actually see what wavelengths the detector can detect. And all I'm gonna do is use the preamplifier for the INSB detector up here. I'm just gonna disconnect the INSB from it and then run some clip leads from the pins here over to my little photodiode that's gonna be inside the sample compartment. And I'm gonna have to tweak the gain settings using this little dip switch right here. I'm gonna have to max it out completely because there's no way that this little photodiode is gonna be as sensitive as the INSB detector up here. But now all I gotta figure out how to mount it in the sample chamber. And my solution for that is a little MacGyver-y. I have this card right here that is an adjustable iris. It's got a little lever on the front. And all I did was I put the photodiode in the center of that iris and then used a rubber band here to close the iris on the photodiode. That holds the photodiode perfectly centered in the optical path. Then I just gotta put some little clips on the leads coming off of the detector, and that's it. That was like a super easy setup. All right, now that everything is kind of plugged in and working, let's take an actual spectrum here. And so I'm gonna come down to here and change my detector to the PDT detector that I defined earlier. Now from experience, the more scans, the better. So we're actually gonna bump this up to about 40 scans. We are gonna leave the scan velocity at 0.5 centimeters per second. And let's just go down here and rename the file to photodetector1. Sure, why not? So let's just go ahead and hit enter on that. It's gonna have to reconfigure the system. So we're gonna see some shutters move up and down. It's gonna reorganize things. Essentially, it's gonna have to steer the beam over to the new detector that's on the right side. And then once it gets done with that, it's gonna start taking scans. We're gonna see this remaining scans, 40 out of 40, start counting down. Yeah, there it goes, 39, 37. And if we look over on the oscilloscope, I actually have it hooked up to one of the test points on the preamplifier, and we can see the interferogram showing up on the scope. So that detector is actually detecting the modulated light that's coming into it. So we're gonna get like a proper spectrum out of this. That's excellent news. And here we go, down to 4, down to 1, and there we go, computing the FFT. As soon as it says ready, we can actually take a look at this in the display menu. So we'll just hop into here. It automatically filled out the name for me, photo1.spc. I'll go ahead and hit return on that, and there we go. That is a spectrum of the Bendix G-15 photodiode. That is awesome. All right, now a couple of things to note here. There's this little tower right here, and if we put my cursor over that, that's right at 15,800 wave numbers. That is the helium neon laser that is used as the primary metrology laser within the interferometer here. A little bit of that light is bleeding over into the detector, and well, we can just ignore that. That's just a peak that we just don't have to pay attention to. But the main peak of energy way over here is what interests me. So we can see that hits at 10,500 wave numbers. And if I look at my little cheat sheet here, that's dead square in the middle of the near infrared. Now, it's entirely possible that there is more bandwidth and signal up in the visible region over here that we're seeing is very low. And I just need to swap out to a different beam splitter to actually see that. But seeing the peak of energy right here squarely in the near infrared, I think that this photodiode is a silicon photodiode. I mean, the spectrum looks very similar. And I think that it actually has a peak detection range in the near infrared. But what this doesn't tell us is the modulation frequency capabilities of that photodiode. To figure that out, I'm gonna have to take a lot more measurements. The design of this FTIR means that the mirror has to move up and down, but I can control how fast that mirror is moving up and down. And so if I take multiple measurements at different speeds, I can start to get an idea of what the modulation frequencies of this photodiode is. Oh, I love a good spreadsheet, man. I spent most of yesterday taking a bunch of measurements and putting them all into this singular spreadsheet here. The goal was to try and figure out what the frequency modulation limit of this photodiode was. So I can do that by moving the moving mirror at different speeds. And I took measurements at 0.3 centimeters per second, 0.5, 0.7, 1.0, and 1.5. And we found that limit, because at 1.5 centimeters per second, It's dead. The photodiode simply can't keep up. So I took the remaining 4 and charted them out into a little chart here so that I could get all 4 onto the same chart, because as excellent as this PDP-11 software is, I can only do 2 spectrum at the same time and overlay them. So I really wanted to see all 4. And if we look at this one, we can see that 0.3, 0.5, and 0.7 are all essentially identical. At those speeds, the photodiode is perfectly happy. But once we get to 1.0 centimeters per second, we have a massive drop in intensity. So now we're starting to see that point at which we get to a little too fast for that photodiode to keep up. And since we're looking at peak wavelength in wave numbers, which is inverse centimeters, and the mirror is moving in the speed of centimeters per second, a lot of the units cancel out here. And the total optical path that this thing has to go through means that it has to go up and back. So we take our mirror movement speed, multiply it by 2, and then multiply that by the peak wavelength. So if it's 0.5 centimeters per second, we're going to do 0.5 times 2, then multiply that by 10,500, which is where our peak energy is. And of course, that comes out to 10,500 hertz. So if we move the mirror faster, like 0.7, that's now 14,700 hertz, and we move it even faster at 1 centimeter per second, that comes out to 20,500 hertz. But we can see the trend here. And actually, even at 20 kilohertz, I think your total amount of energy has come down far enough that I wouldn't really want to use any signals faster than 20 kilohertz on that photodiode. So what does this mean for the Bendix G-15 itself? That paper tape is moving along at a decent clip, 200 characters per second. But actually, it's even worse than that, because the photodiode has to detect the change in light on a data hole and fully stabilize before the clock hole starts to transition. And so if we put some numbers on this, the data holes are 1.82 millimeters, the clock hole is 1.17 millimeters, which means that that photodiode has to detect the change of light and stabilize in just 0.65 millimeters. Now the tape is moving at 200 characters per second, which is 20 inches per second. And since I'm doing everything in the metric system, that comes out to 508 millimeters per second. So you do a little bit of division here, and that comes out to around 780 hertz. So 200 characters per second is not getting anywhere near the limitations of the photodiode, which makes sense because the Bendix G-15 also has a separate peripheral that is a phototape reader that sits on the desk that reads at 400 characters per second, double the speed. So that's going to need to deal with modulation around 1.4 kilohertz. But again, these photodiodes are absolutely crushing it. We could send that tape so much faster that at that point, the only concern really comes with the tape itself falling apart and shredding and tearing as you spin it faster and faster and faster. I'm totally blown away at how fast these 70-year-old photodiodes can react. This is absolutely incredible. I had a blast. I mean, this is an indication of how old I'm getting, because I had an incredible amount of fun making spreadsheets and graphs in this episode. Oh, it was so much fun though. So I want to thank you all so much for hanging out with me today, and I hope to see you in the next one.